Hey, I'm Mitchell, and welcome to another video in the RSP Education series. Today we're going to talk about electricity. It's the invisible force that powers everything around us. But did you know that there was a battle over how that power should flow? A war between two of the greatest minds in history. That's Thomas Edison and Nikola Tesla. This battle determined the very way we use electricity today. In the late 1800s, Edison fought dirty, even electrocuting animals, just to prove his direct current, DC, was superior. But Tesla's alternating current, or AC, ultimately won the war, lighting up entire cities and shaping the modern electrical grid. Today, AC and DC power are everywhere in industrial automation, but do you really know the difference and why it matters? This is the foundation of industrial automation, and if you want to truly understand the systems that keep factories, power plants, and automation running, then you need to take a deeper look. If you like this kind of content and want more educational videos, please like and subscribe. Also, this video is for educational purposes only. Always consult a professional for your application, since RSP Supply is not liable for any misuse of this information. With that said, let's get right into it. So let's start with DC power. Think of it like a river that's flowing consistently in one solid direction. This results in a constant voltage polarity. DC stands for direct current. Electrons, which are the tiny particles carrying electricity, these flow steadily in a single direction, from the negative to the positive terminal. Where do you commonly see DC in automation? Well, think about the brains of the operations, like PLCs, which are programmable logic controllers, sensors, and many control circuits. These often are going to run on DC power, but why? It's because DC provides a stable and consistent voltage that's perfect for sensitive electronic components that depend on reliable digital signal processing and exact analog measurements. Think of it like a steady heartbeat of your control system. In ideal DC, the voltage is a flat line. However, in real-world industrial DC systems, especially after rectification from AC, we're often going to be dealing with a ripple, which is a small voltage fluctuation around the desired DC level. This ripple and how effectively we filter it is a key design consideration. Imagine you have water flowing back and forth in a pipe. This is like alternating current, AC. Now, you need the water to flow only in one direction. This is like direct current. Rectification is a process that makes this happen for electrical current. In simpler terms, rectification is a process of converting alternating current, AC, which periodically reverses direction, into direct current, DC, which flows in one direction. So why do we need to rectify AC power in the first place? Most of the electrical power that's generated and transmitted around the world is in the form of AC. This is because AC is more efficient for long-distance transmission and can be easily stepped up or down in voltage using transformers. However, many electronic devices and systems still require DC power to operate, like PLCs, sensors, actuators, HMIs, which are human-machine interfaces. How does rectification work? The key component in rectification is the diode. A diode is like a one-way valve for electricity. It's going to allow current to flow easily in one direction, a forward direction, and blocks or severely restricts current flow in the opposite direction. Rectifying DC power is a crucial process in electronics. We use diodes in rectifier circuits, either half-wave or full-wave, or center-tapped or bridge diodes to convert AC power into pulsating DC. Filtering, by mainly using capacitors, is going to smooth out the pulsating DC, and voltage regulators stabilize the output voltage. This processed end result DC power is then used to operate a vast array of electronic devices and systems that rely on a constant unidirectional flow of current. Now for AC power. Imagine instead of a river, the metaphor used for DC power, you have something like a tide going in and out, back and forth. Here, the electrons don't just flow in one direction. They constantly change direction, oscillating back and forth in a cycle. This back and forth movement happens very rapidly, typically 50 or 60 times per second, depending on where you're at in the world. In the US, we use 60 megahertz. This sinusoidal waveform is characterized by its frequency, typically 50 hertz or 60 hertz. 60 hertz here in the US in industrial settings. Its peak voltage, and importantly, its RMS, or its root mean square voltage, which represents the effective voltage value for power calculations. Understanding RMS versus peak is crucial for component selection and system safety. Furthermore, polyphase AC systems, typically three-phase, are prevalent in industry. They offer smoother power delivery, higher efficiency for motors, and reduced torque ripple compared to single-phase AC. So the battle between AC and DC wasn't just a war of ideas. It actually shaped the very backbone of modern automation. From the towering power grids that light up entire cities to intricate control circuits that keep industrial processes running with pinpoint precision, AC and DC power work together to drive the world forward. But this is just the beginning. The real question isn't just what AC and DC are, it's how you use them to optimize automation as a team, to improve efficiency, and to solve real-world engineering challenges. That's exactly what we'll dive into in part 2. For hundreds of thousands of other industrial automation products, please go to our website. And for more information and educational videos, go to our website, rspsupply.com, the internet's top source for industrial hardware.